Hello everybody and welcome to this Copernicus Marine Service training. My name is Etienne Seig from Noveltis, and today I'm going to show you how to visualize sea ice concentration and estimate the sea ice classes along a ship route in the QGIS software. The Baltic Sea is an almost enclosed sea and constitutes the only access to the ocean for several European countries, making it one of the busiest seas in terms of marine traffic. Every winter, the area experiences sea ice that affects shipping routes. It constitutes a threat to the navigation, and analyzing the sea ice condition in the Baltic Sea is of prime importance to decide which type of vessel should be used to sail in this area. In this context, the operational, precise and reliable Copernicus Marine Service products for the Baltic Sea are a great asset to analyze and forecast the sea ice condition in the region and ensure safety at sea. We will see how to use them in a QGIS software to make the most of them. As all of these products have a NetCDF format, which is convenient to handle several variables, Noveltis has developed a plugin to easily exploit this data. This training is directed toward an experienced audience already familiar with Copernicus Marine Service sea ice product and QGIS software. All material useful for this training are available with the user manual of this training on the Mercator Ocean user platform. First of all, we are going to open a new project in QGIS and load the background for this project. To do so, you just have to go to Layer here, Add Layer. We are going to add a WMS layer and connect to the map server demo here. Once it is done, we can just select the blue marble layer and add it to our project, and then close this window. Now we are going to import to our project the sea ice concentration product from the forecast and analysis model of the Copernicus Marine Service. In this part, we are going to use this product only with the QGIS software and not with the plugin, in order to have all the time frames of one product in only one layer. So the project we are going to use is the analysis and forecast Baltic Sea model, which is a physical model providing forecast for the physical conditions and sea ice in the Baltic Sea, with a spatial resolution of 2 kilometers and a temporal resolution of a day. To import this data, we are going to click to Layer, Add Layer, and we are going to add a NetCDF file, which is a raster layer. Here you can browse into the directories and load the Baltic Analysis Forecast sea ice data from the 27th of February to the 4th of March of 2022. Here we can click on Add, and we have to select in the popping window the sea ice area fraction here. Click on OK, and then you can close this window. Now we are going to tune the representation of the sea ice concentration we just have added to our project. To do so, we are going to right click on this layer, open the properties, and in this window we are going to change the render type to single band pseudocolor. Now you can select here in bounds the time frame you want to display. For example, if we want to display the 27th of February, the first time frame of this data, we are going to select the bound 1 here. We are going to set the minimum value to 0 and the maximum value to 1, which means a total concentration of sea ice. And now we are just changing the color ramp and invert it from blue to red. Now you can click on apply and OK. If you zoom to the Baltic Sea region here, we can see that we have the representation of the sea ice concentration on the 27th of February 2022, forecasted from the Copernicus Marine Service. Now we are going to show you how to extract the sea ice coverage time series on exact locations, on specific points. To do so, we need to install a new plugin, which is Numerical Digitize. So you are going to click on plugin here, manage and install plugin. And in this window, we are going to find Numerical Digitize plugin. Here it is already installed in my case, but you just have to select it and click on install plugin. Then you can close this window. Once the plugin is installed, you have new options which are available in your QGIS, and we are going to use them later. Now we are going to create a new layer, a new shapefile layer, which is going to contain the new points where we want to extract the sea ice coverage time series. To do so, click on layer, create layer, and here we are going to select new shapefile layer. The name of this layer is gonna be point extraction, and you can save it wherever you want. And you just change the geometry type to point. And then click on OK. So now we have a new shapefile layer, point extraction, here. We want to add some points to this layer. To do so, we are going to toggle to editing mode here and click on the pen icon. And now we can define several points location in the Baltic Sea following there are two methods, or you can use this icon here and draw points, or you can select this option and to type longitude and latitudes of each point you want to add to this layer. In my case, I will select this first option, so I activate this option, and now you can just add some points in areas of interest. So I'm going to select the first one here and add the 0 index here, add another point here, 1, another point here, 2, and the last point will be here, 4. Okay. So now we have defined 4 points, and if you want to change the location of some points, you can use this option here and then select a point and just move its position. Now we can just change the and close the editing mode of this shapefile layer and save the changes to the point extraction shapefile layer. Click on save. Now we are going to extract a sea ice concentration time series from this layer. To do so, we need to use a function in the processing toolbox. So you just have to open the processing toolbox here. And now we are going to look for the sample raster values function here, and you can double click on it to open it. So now we are going to extract time series from these points, these 4 points here, and we are going to extract values from the raster layer, which is this one, the sea ice concentration on the 27th of February 2022. Now we are just going to change the output column prefix to sea ice concentration underscore D. Then you can just run the function and close this window. Now in this output layer sampled, each defined point here has the sea ice concentration time series as attribute. For example, if we open the attribute table of this new layer, we can see that we have for each point the sea ice concentration on the first time frame, second time frame, third time frame, and so on. So on the 27th of February, 28th of February, 1st of March, 2nd of March, and so on. So here we have shown to you how to extract a time series of a specific variable on specific points, and how to do this this processing on QGIS, which is typically something we can do on Python also, but here you can do all of these operations in QGIS. Then you can close this attribute table. Now we can just add some information to this layer and add the coordinates, longitude and latitude, of the points we have defined before. To do so, you just have to look for the add geometry attributes function, double click on it, you select the input layer sampled, and then you can just click on run, close. And now if you open the attribute table again, you have the time series of the sea ice concentration on each point from 0 to 4, and the x and y coordinates in degrees, longitude and latitude. You can now close this window. We can just rename this layer, right click on it and rename layer to sea ice concentration sampled on some points with geometry coordinates. Okay. This layer can be exported and saved as different formats. For example, we have extracted time series of sea ice concentration variable, and we can have an interest of extracting this layer as a comma separated value to post-process it on another software. So you can right click on this layer, select export, save feature as, and here select the comma separated value format type a file name, for example, points sea ice extraction, and then just click on OK. Now you have saved the time series of the sea ice on 4 points to your documents. Now we are going to, in the second step of this training, to do the computation of the mean sea ice coverage over areas defined by some additional documents. We are going to use the Baltic Sea Boundaries, which is a shapefile document produced by the International Hydrographic Organization, IHO. To do so, we are going to import this layer, so click on Layer, Add Layer, and the shapefile is a vector layer, so add vector layer. You are going to browse into the directories to find the IHO.shapefile and open it. Click on Add and then close this window. We can see that the IHO is dividing the Baltic Sea in several areas. Here, between Denmark and Estonia. Here, north of Denmark. Here, the Gulf of Riga. Here, the central Baltic Sea. Here, the Gulf between Sweden and Finland, for example, and so on. Now we are going to compute some stuff over each area. To do so, we are going to use the processing toolbox again, and in the raster analysis section we are going to select the Zonal Statistic function. You can select it. Now we are going to select the shapefile of the boundaries of the Baltic Sea as an input layer. The raster layer which we are going to use is still the sea ice coverage for the 27th of February. So the bound 1. And we are going to change the output column prefix to stats because we are going to compute statistics, and here we are going to change the statistics to calculate. So click on the 3 dots here, and we are going to select mean, minimum, and maximum statistics. Click on OK, and then you can run this function and close this window. So several statistics have been computed over each region of the IHO shapefile. So the resulting zonal statistics layer now has the mean, minimal, and maximal values of the sea ice concentration for each area. And if we want to reach this data, we just have to open the attribute table, right click on the layer, open attribute table of this layer, and here you can see that you have access to these informations with the maximum values of sea ice concentration, minimum values, and the mean values here for each region. Now we are going to see how to compute sea ice concentration which are higher than a threshold on a specific daytime on the 27th of February 2022. It's the following of what we are going, which is processing sea ice data contained in projects from the Copernicus Marine Service. To do so, we are going to create a new raster layer, and to do that, to apply a threshold of the sea ice concentration, we need to convert data which are from 0 to 1 in this layer, concentration which are from 0 to 1, to concentration which are from 0 to 100%. To do so, we are going to work still on this layer, so take it on top of the other layers that you can uncheck, and we need to rename this layer to be clearer. To do so, right click on it, select rename layer, and we are going to rename it sea ice concentration. Now we are going to apply some operations to convert this layer from 0 to 1 to 0 to 100. So we are going to multiply each value of this raster layer by 100. To do so, open the raster calculator here and select the first time frame of the sea ice concentration layer and multiply it by 100. Here we are going to change the output layer name and call it sea ice cons 100. Save it. Let the output format to GeoTIFF, and here you can click on OK. So now we have a new layer with sea ice concentration from 0 to 100. We are going to convert this layer from raster to vector because it's easier to compute jointure and intersections between polygons, and so with vector layers. To convert this new layer to to a polygon, we have the option of clicking on raster here, conversion and polygonize, and we are going to polygonize the sea ice cons 100 layer. Now we are just going to change the name of the field to create to sea ice cons. Change the output name. Here. Sorry, here. You can save this file, which is gonna be sea ice cons polygon point shape. Here I have already done this step, so the file is already existing, but I'm going to replace it. And here you can click on run. Once it is done, you can see that this new layer is a polygon layer, a vector layer, which several polygons here, with several levels of sea ice concentration. But this conversion can have some issues if we check the validity function. So in order to assess the quality of the resulting polygons from the raster layer, we can just use the check validity function here, and if I select this resulting layer and click on run, I can see between all these layers that only some polygons are valid polygons here in orange. All the other layers here in red are invalid polygons. So there have been a problem during the conversion to this layer in raster to this layer in polygon. So we are going to fix these issues. To do so, we are going to look for the fix geometries function and apply it on CIS cons polygon layer here, and the resulting layer will be CIS cons polygon fixed. Click on run. Sorry, you need to select a file and save it as a new file and click on run. Now you can close. You can remove these layers of the first diagnostic on the CIS cons polygon layer, and we are going to do the same diagnostic with the CIS cons polygon fixed to see if this function has done what we expected. So if we go to the check validity function and apply it to the CIS cons polygon fixed, you can run it, close, and you can see that there are some there are only valid outputs here, so all the polygons are valid. So now we can just delete these 3 layers of diagnostics, and we are going to work with this layer of CIS concentration polygon fixed. Now we are going to explore this layer. For example, if you select the information tool here and click on the polygons of this CIS concentration layer, we can see that we have CIS concentrations in integers, so with 98% of ice in this polygon, 99 in this one, 95, 96, 7 on those polygons, and so on. So we have converted this raster layer in polygon, and we have also converted from concentration from 0 to 1 to 0 to 100. Now you can go back to this tool here, and we are going to apply in this new polygons layer here. We can deactivate the other layers. We are going to work with this new layer, and we are going to filter this layer because we want to apply a threshold of, for example, 70% of ice concentration. So we are going to right click on this layer, apply a filter of CIS concentration up or equal to 70%. Here you can just click on test to see the impact of this filter. OK, and click on OK. Now we can see that the remaining data are polygons where the CIS concentration is up to 70%. Now we are going to merge all polygons which have the same value of sea ice concentration together. For example, we want only one polygon for 100%, one polygon for 9900% of sea ice coverage. To do so, we are going to use the vector here geoprocessing tool, which is named dissolve, and apply it to this layer here, sea ice cons polygon fixed, which is filtered to concentrations which are higher than 70%. Now you can click on Run and close. We now have a single polygon covering the area experiencing a sea ice coverage higher than 70% in the Baltic Sea. This is this polygon, this red polygon, which have values from 70 to 100% of sea ice coverage. Now we can just add a last step, so we are going to compute the area covered in sea ice by more than the 70% threshold. So select this merge layer and toggle to the editing mode. Now we are going to right click on this layer and go to properties, and in properties we are going to open the field calculator. So we are going to go to fields here and open the field calculator, and we are going to compute a new field, which is area in squared kilometers, and we are going to type the expression area and multiply it by 10 exposed minus 6, and to obtain an area computed in kilometers. Now we are going to click on OK. Here you have the preview of the results of the area, and click on OK, apply and OK. Here we can just close the editing mode and save the modifications. So now if we go to this layer here and open the attribute table, we have the area of the sea ice concentration up to 70%, which is equal to 38,000 and almost 600 square kilometers, which represent 10% of the Baltic Sea area, which was covered by more than 70% of ice on the 27th of February 2022. Now the first part of this training is finished, and in the second part we are going to treat about sea ice thickness along ship routes. So in this second part we are going to focus on sea ice thickness, and we are going to use the Copernicus Marine Service plugin to display the data contained in the Baltic Analysis and Forecast physical model between the 27th and the 4th of March 2022. So I'm going to show you how to import new data. So to import data to this plugin, you just have to click on the plus icon here and import the data containing the sea ice thickness from the Copernicus Marine Service. Click on Open. Here you have access to several informations, the variables, name, dimensions and units of your data. And you have also access to metadata with the resolution of the model and some informations of the creation on this data. We are going back to the NetCDF panel here and the variable panel here. We are going to focus on CI thickness. We are going to load the CI thickness for the 7 days between the 27th of February and the 4th of March. Right click on it and select add layers. Here you can just select the first time step with left click and press the shift key on your keyboard and select up to the 4th of March. We are going to import all these layers. Click on add and close. Go back to your QGIS project and you can see if you deactivate the previous layers and just here close the information option, we can see that we have added to our project the CI thickness layers from the 27th of February to the 4th of March 2022. You can just check and uncheck the layers to see the evolution of the CI thickness during those days. Now we are going to change the palette of this first layer. Right click on it, go to properties. We are going to set the maximum value to 90 centimeters and just ensure to invert the color ramp from blue to red. Click on apply and OK. Now you can just copy this style. Right click on the first layer, style, copy style, and apply it to the other layers of CI thickness and paste style. So now we have highlighted the thicker CIs up to 90 centimeters in red, and you can see the evolution again during the first week of March. Once we have duplicated the style of the CI thickness of the first day of the week to all the other layers, we are now going to classify the pixels of these layers. To deal with CI's data, it's usual to classify CI thicknesses between intervals. This is why we are going to create classes of pixel whose CI thickness is in between user-defined thresholds. To do so, we are going to use the processing toolbox and look for the reclassification by table function. Double click on it to open it. Here we are going to select the first layer here, the one corresponding to the 27th of February 2022 on the first band, and we are going to create a reclassification table here. To do so, click on the dots here, and here we are going to add 6 rows. So the first one will be the first class from 0 to 0.20 with a value of 20 centimeters, and so on until 1 meter. And now here we are going to create a class for no values with a value of 101. Once it is done, you can click on OK here and just run this function. And here close the reclassification by table function. So here we have thicknesses order from 0 to 100 centimeters by classes defined by the user. The choice of the classes is up to you, so if you want you can try several classifications, and the output layer resulting from the classification is a raster layer where the pixels are gathered into the 6 different classes we have defined. Now, to perform further analysis, we need to convert our reclassified raster to a vector layer, a vector layer, yes. And as we did before in the first part of this training, we need to fix the geometries after that. So now we are going to select vector geoprocessing. Sorry, no, this is a raster layer and we need to convert it to a vector layer. So go to raster, conversion, and polygonize. Here we are going to convert this reclassified raster on the band 1. We are going to select the field to CI thickness and just give a name to the vectorized layer and save to file. So here again name it CI thickness polygon layer. Here I have already done the treatment, so it already exists in my computer, so I'm just going to replace it. And here you just have to run this function, and now you can close this window. So here we have the vector layer corresponding to the classified raster layer of CI thickness between 0 and 100 centimeters. Once the conversion is done, we are going to fix the geometries and the polygon geometries of this layer. So look for the fix geometries function and open it, apply it on the CI thickness polygon layer, and the fixed geometry layer will be this one, CI thickness polygon underscore fixed. And now you can click on run. Okay. Now we are going to, as we did before, we are going to merge the values of CI thickness contained in this layer of polygons by classes of CI thickness. For example, I'm going to merge all CI thickness up to 20 centimeters together, up to 40 centimeters together, and so on. To do so, here we can just activate the last layer to be clearer. Close the processing toolbox. To do so, we have a vector layer here, so we are going to select vector, geoprocessing tools, and again dissolve option. We are going to apply it on the CI thickness polygon fixed layer, and here we are going to merge the CI thickness fields, so you just have to select the CI thickness here, click on OK, and we can launch this function, which is going to gather polygons which are in the same classes of CI thickness. Click on run and close. So now it's not clear, but if we go to the information option, we can see that all the 40 centimeter class CI thickness class is gathered together, and so on for the 0. Here, oops, I have the 0 polygons here and the 20 centimeters polygon, 40 here, 60 centimeters class of sea ice thickness here, and so on. So we have gathered all the individual polygons of the class of 60 centimeters together with this dissolve option. Now we are going to represent this resulting layer, which categories of colors to have on the map, different colors by categories. So to do so, we are just going to go back to the pan map option to move the map. We are going to open the properties of the resulting layer here and go to symbology. Here the representation is by single symbol and colors, but we want to use the reclassification we have done in this layer here, and we want to use this categorization to represent each class on a different color. So we are going to select categorized here and select a categorized representation according to the sea ice thickness value. Now you can click on classify here to find back your categories you have done on this reclassified raster initially. We are going to change the color bar here and select the red one and just change the class of 0 centimeter sea ice thickness to transparent. So double click on the first color and on the resulting panel, go back, select the color again and drag the opacity to 0%. Now you can click on OK, OK, apply these colors and click on OK. If we activate only the last layer, the dissolved layer, which contained sea ice thickness classes, we can see that here we have all our classes of sea ice thickness reorganized and reclassified as we did in this step. Now we have each class of sea ice, and we can use this information to draw a safe ship route from one harbor of this gulf to another. To do so, we are going to use data from the World Port Index, which is a global database which provides harbor locations around the world and multiple additional information such as their size, country, etc. So this shapefile is available is made available by the National Geospatial Intelligence Agency on its Maritime Safety Information website. To import this shapefile, we are going to click on layer, add vector layer, and browse to the WPI shapefile here. Click on open and add and close. So you can see here you have brown dots all over the coast representing the harbors of each country. Now we are going to change the style of this layer. So here you can close the processing toolbox and zoom here on the northern Baltic Sea. So here we are going to change the style of representation of these harbors. So right click on this layer, open properties, and here we are going to load a style available on the Mercator Ocean user platform. click on style, load style, and here we are going to browse to the style underscore WPI underscore size.qml style file. Open it, click on load file, apply this style, which is representing dots with size according to the size of each arbor, and from large to very small arbors, and with their names. Click on apply and OK. So now you have access to all the arbors of the coast of the Gulf between Sweden and Finland. And for the example, we are going to create a route between two arbors here. We are going to create a route between the arbor of Kaskinen here, and we are going to Luleå here in Sweden. To do so, we need to create a new shapefile layer to gather the points of our ship route. So here we are going to click on layer, create a layer, and create a shapefile layer. This file name will be, for example, points of the ship routes, and the geometry type is gonna be point. Okay. Now you can click on OK, and here you can take on top of your layer panel the point ship route layer. To add points to this layer, we need to toggle to editing mode here. Click on the pen icon, and now if you select this add point feature option, you can add points to the point ship route shapefile layer from the Kaskinen arbor to the Luleå arbor in Sweden. And we are going to iterate the names for each dot. First dot is 0, okay, then 1, and so on. We are going to try to avoid thicker sea ice zones. So for example, I try to stay in the soft pink here. Because it's not the same type of icebreaker and boats to cross each category. Seven, and now we are going to Luleå. 8. Okay. So now you can see that you have drawn a ship route avoiding thicker sea ice categories from Kaskinen to Luleå. Once it is done, you can just close the editing mode and save modifications to your shapefile layer here. Now you can just change the representation of each dot to see it better on your project. So I'm going to select this symbol, which is clear. And here we can see our ship route. Okay. Now we are going to add, if you check this layer and the attribute table, you can see that you have the IDs here of your dots. Here I've made a mistake between the indexes, but it's not important. and we want to add for each point the geometric coordinates, longitude and latitude. So we are going to use the add geometry attributes function. So type add geometry and select this function, and we are going to add geometry attributes of the points of the ship route to this layer. Click on run, and then you can close this window. So if we open the attribute table of this resulting layer, we can see that for each point we have the x and y coordinates corresponding to longitude and latitudes in degrees. It can be useful to extract this data as at a comma-separated value format, for example, to post-process them or give them to someone who needs the information of the ship route. Right-click on this layer, select Export Save Feature As, and the format you have several formats available, but select the comma-separated values, and here you can just name its points coordinates for the ship routes. Save and click on OK. Now the last step is to convert this layer with points to a layer of lines. To do so, we are going to use the points to pass function here. Open it. We are going to select the added geom info, so the points layer with geometric informations as an input layer, and click on run and close. And here you can see that you have the lines representing the route of your ship here. We can just tune the representation of this path to have something more visual. To do so, we can just change the color and the thickness of the lines. So double click on passes or right click and open properties, and we are going to use dashed representation of the path. Change the color to white and just increase a little bit the width of the dash. Apply and OK. Here you can see that you have a clear visual of the ship route you have drawn using the informations of the CI thickness categories to draw the route. So that was the last step of this training. So we have seen how to display CI's concentrations and CI's thickness, and to process them, use all the data stored in the different variables of the Copernicus Marine Service products. And here we have used a forecast analysis model to process this data and draw a ship route avoiding the thickest sea ice conditions in order to protect people and boats. So you can use this scenario with other data and other time. Thank you for your attention, and see you later.